Welcome back. Today we're going to talk about the singular value decomposition. If you have an n by n matrix, you can talk about its eigenvalues and its eigenvectors, and that leads to the Jordan form and lots of information about the matrix. And remember, an eigenvalue and an eigenvector are given by this equation. Now, the question is what to do if A is not square, and that's what singular value decomposition is about. And the problem is that this equation AV equals lambda V doesn't make any sense if A is not square, because A is a map from Rn to Rm, and if n is not equal to m, these are two different vector spaces. So what do? Well, that's what the singular value decomposition is all about. It's basically a substitute for the notion of eigenvalues and eigenvectors. And the basic idea is the following. If you have any m by n matrix, we're talking about real matrices here, by the way, you can get a symmetric matrix out of it by taking A transpose A. And this is an n by n symmetric matrix. And so you can, I'm just showing here that that's you get an n by n matrix this way. And let me remind you that A transpose A is symmetric. That's easy to see. I even say it's obvious. And it's also positive semi-definite. We've talked about this before. That's slightly less obvious, but it's true. All of its eigenvalues are greater than or equal to 0. So this matrix A transpose A is a particularly nice kind of matrix. Remember, the spectral theorem applies to a real symmetric matrix. And you all remember what the spectral theorem says, I know, so I don't need to repeat it. Well, I'll repeat it anyway. The spectral theorem says that when you apply it to this symmetric matrix A transpose A, that it's diagonalizable. And it's diagonalizable by a basis which is orthonormal. In other words, it has this matrix has an orthonormal basis of eigenvectors. And furthermore, the eigenvalues are all real. Well, that's true for any symmetric matrix, but the fact that this matrix is positive semi-definite says not just that they're real, but they're actually greater than or equal to 0. So we have a bunch of eigenvalues which are positive or maybe 0. So that's sort of the starting point. Instead of looking at A, we're going to look at A transpose A. Okay, so we have our m by n matrix. We set K is equal to A transpose A. That's an n by n matrix, symmetric, and with it's positive semi-definite. So it has real eigenvalues, which are, I'll label them lambda 1 through lambda n, which are greater than or equal to 0. That's basically repeating what I said on the previous slide. And now here's the definition. The singular values of this matrix A are the following. What you do is you take the square roots of the lambda i's which are non-zero. So they're usually labeled sigma I, and you take the lambdas which are strictly positive, and you take their square roots. And you order these, it's standard to order these in decreasing order. And so you have sigma 1 is greater than or equal to, and so on. And there might not be n of them. So the singular values are some smaller number of sigmas, up to n sigmas, all of which are positive real numbers. Okay, so that's just the definition. It's the square roots of the positive eigenvalues of the matrix A transpose A. And the singular vectors are, by definition, the eigenvectors of this matrix K associated with these eigenvalues. And since K is symmetric, you can take them to be orthogonal or even orthonormal. That's not so important. Okay, let's look at an example. So let's take a non-square matrix, say the matrix 1, 2. So here m is 1 and n is equal to 2. It's important to keep track of m and n, otherwise you get confused. A transpose A is this matrix, and let's see, how big is this? This is supposed to be n by n, which is to say 2 by 2. So let's make sure we get the right size here. It's 1, 2, 2, 4. This symmetric 2 by 2 matrix. And what are its eigenvalues? This is the matrix K. Its eigenvalues are the solutions to this equation, which is to say lambda squared minus 5 lambda is equal to 0. So the eigenvalues are 0 and 5. Okay, so when lambda is equal to 0, it doesn't count. So the only singular value is square root of 5. There's one singular value, square root of 5. And the corresponding singular vector is the eigenvalue associated with this eigenvalue. And to do that, you subtract 5 from the diagonal and find the null space. And you see that you can take singular vector to be, for example, 1, 2. Okay, so we're not going to pay too much attention to the singular vectors. The important thing is these singular values, square root of, in this case, square root of 5. All right, let's do another example. Let's do the same example, except let's make it a column vector. So now m is 2 and n is equal to 1. And so A transpose A now is A transpose A looks like this. This is supposed to be a 1 by 1 vector. And let's see, you get the 1 by 1 vector 5. That's a 1 by 1 symmetric matrix with a single eigenvalue 5. So it has one singular value, same as before, which is the square root of 5. And the eigenvector is just the 1 by 1 matrix. You can take any vector you want, non-zero vector, like, for example, 1. Okay? So these two matrices, A and its transpose, have the same singular values, same number of them, and it's just, in this case, just 1. Okay, well, let's look at an example of a square matrix. A square matrix has its own eigenvalues and eigenvectors, but it also has singular values and singular vectors. And how are they related? Well, let's look at an example. Suppose I took a just 2 by 2 matrix, 0, 1, minus 1, 0. That's a perfectly good 2 by 2 matrix. It has its own eigenvalues and eigenvectors, and we all know that the eigenvalues are plus or minus I. So they're not real. So now if you do the singular value decomposition and you take A transpose A, you get the identity matrix. So the singular values, there are 2 of them, and they're both 1. And so these singular values, which are 1, don't have anything to do with these eigenvalues, which are not even real. So these are really not the same. So don't make the mistake of thinking that for square matrices, singular values are the same thing as eigenvalues. All right, well, having warned you about that, I'm going to backtrack a little bit. What about if A was symmetric to start with? So let's take an n by n symmetric matrix. Maybe for these, the singular values and the eigenvalues are the same, or at least closely related. So, for example, what if A was diagonal? So suppose A was a diagonal with A1 through AN on the diagonal. And then A transpose A, of course, is A1, this diagonal matrix times itself, which is to say it's the squares going down the diagonal. And so that is to say that the eigenvalues of K are these numbers A1 squared down to AN squared. That's what these lambdas are, the eigenvalues of K. And so therefore the singular values are the square roots of those. That is to say, let's suppose that they're all greater than 0, so I don't have to worry about the 0 business. So then the singular values are the square root of A1 squared, which is A1. But be careful. If A1's negative, you only want the positive square root. So the square root that we're talking about is the absolute value of A1. And so the conclusion is that the singular values are the absolute values of the eigenvalues. The eigenvalues of the original matrix. So they are very closely related, but they can't be exactly the same because a symmetric matrix can have negative eigenvalues, but singular values always have to be positive. So the simplest thing could be that, yes, you just take the absolute values of the eigenvalues. And so, well, that was for diagonal matrices, but general symmetric matrices, it's exactly the same. If you take an n by n symmetric matrix, then, of course, its eigenvalues are real. You know that by the spectral theorem. And so you write down its eigenvalues, lambda 1 through lambda n. Then the singular values of this n by n symmetric matrix are what? They're the absolute value of the lambdas. Absolute value. But you only keep the ones which are positive. We always throw out singular values which are 0. So, for example, if A was this matrix, then its singular values are what? Well, its eigenvalues are 2, minus 1, 3, and 0. So that says its singular values are 2, 1, and 3. Make them positive and throw away the 0. All right, well, one of the main points of the theory of singular values is something called the singular value decomposition. Okay, so this is one of these decomposition theorems. We've seen a couple of different kinds of these before. It's a sort of nice way of writing a matrix. And in this case, the main point is matrices which aren't square. And so in the past, for example, we had the LU decomposition, and we also have the QR decomposition and several others of this sort, particularly nice ways of writing matrices. So here's the story. You have an m by n matrix, and you compute its singular values, sigma 1 through sigma r. I'm always going to use r for the number of singular values. These are the number of non-zero. These are all non-zero. And okay, and then the fact is that you can write A in the following form. You can write it as P times sigma times Q transpose, where sigma is this R by R diagonal matrix with the singular values on the diagonal. And you're multiplying it on the left by a matrix P, and on the right by this matrix Q transpose. All right, and this matrix P is of size M by R, and the matrix Q transpose is by necessity of size R by N. So let's just check this all works out. The R's cancel and the other R's cancel, and the result is an M by N matrix, which is the size that A was supposed to be. So again, half the game here is getting your matrices to come out to be the right size. All right, so this is the decomposition, and I have more to say about P and Q on the next that's coming up. So this sigma, as I said, is this diagonal guy. And P has orthonormal columns, and Q transpose has orthonormal rows. Okay, I had to kind of squeeze that in there. I'll say it again on the next slide. But that's the singular value decomposition. So here's the picture. This P I've indicated with blue. It's an M by R matrix with orthonormal columns. Sigma is this R by R diagonal matrix, and Q transpose is this R by N matrix with orthonormal rows. I wrote Q here. I should have said Q transpose. And sigma is this diagonal matrix. So that's the singular value decomposition of this arbitrary M by N matrix A. All right, so let's look at an example. So let's do our little 1 by 2 matrix from earlier. M is equal to 1, N is equal to 2. And I saw that this fellow has a singular value. Maybe I should just say one singular value, which is the square root of 5. So R is equal to 1. So I want to write the matrix 1, 2 as what? Let's see. Well, in the middle here, I want to, well, let's see, the matrix P is supposed to be M by R, which is to say 1 by 1. And this matrix in the middle is the diagonal matrix radical 5. And then the matrix on the right had better be, let's see, R by N, 1 by 2. And, well, it's sort of obvious. This matrix P is supposed to have orthonormal columns, so it's just the identity 1 by 1 matrix. And what do you get? You see that this must be the matrix 1, 2 normalized to have length 1, and that's the answer. So that's P, sigma, and Q transpose, respectively. It's just sort of traditional to call this Q transpose instead of Q. It doesn't really matter. Excuse me. Okay, so that's the singular value decomposition of this 1 by 2 matrix A. Okay, well, let's do our transposed example. Suppose A was this matrix. Now you've switched M and N. M is 2 and N is 1. R is still 1 and sigma is still just radical 5. So we want to write 1, 2 as, let's see, now I'm supposed to write it as a R by N, which is 2 by 1. Excuse me. M by R, which is 2 by 1, times sigma, which is 1 by 1, times Q transpose, which is R by N, which is 1 by 1. So now the 1 goes over here, and now the other guy goes over here. And so now you've just switched the role of P and Q transpose. So that's just sort of an obvious general fact. If you have the decomposition for if you have the singular value decomposition for A, you just take the transpose and switch the order as usual to get the singular value decomposition for A transpose, and in particular the sigmas are the same. Okay, so let me give a formal statement of the singular value decomposition theorem. I basically said it before, but I'll just say it again for emphasis and to have it all down on one piece of virtual paper. The singular value decomposition theorem says the following. We have A is an m by n real matrix, any m by n real matrix. Attached to it is this matrix K. It's A transpose A, which is an n by n symmetric matrix. It's positive semi-definite. This is all automatic. And so you can compute its eigenvalues, and by taking the square root of the non-zero ones, you get the singular values labeled sigma 1 through sigma r. And I'm just reminding you that the sigma i's are the square roots of the positive eigenvalues of k. All right, so that's the singular values. And then the theorem says that you can write A as P sigma Q transpose, where P is an M by R matrix with orthonormal columns. And Q transpose is an R by N matrix with orthonormal rows. And sigma is this diagonal singular value matrix, sigma 1 through sigma r on the diagonal. This decomposition always exists. All right, so let's do another example. Let's do a little bit more non-trivial example. Now let's take a 2 by 3 matrix like this, 1 1 0 0 1 1. So A transpose A is, let's see, n is 3. So this is going to be a 3 by 3 matrix, and turns out to be equal to this. And so you compute the eigenvalues of this 3 by 3 matrix, and I'll skip the arithmetic and just tell you that the answer is it has two eigenvalues which turn out to be 3 and 1. So R is equal to 2. There are two non-zero eigenvalues, and square root of 3 and square root of 1 is the singular values. Okay, so here is sigma. It's a 2 by 2 matrix. And now P, let's see, M was 2 and N was 3. And so P is supposed to be M by R. So that's going to be a 2 by 2 orthogonal matrix. And on the other hand, Q transpose had better be R by N, which is to say 2 by 3 in order for it to come out the right size. And we're looking for a P and Q which make this true, and I'm not going to say how you compute these, but here's the answer. Turns out that P is this matrix, and this is the matrix sigma, and the matrix Q transpose is the following. It has some radical 6s in the denominator, and it looks like this. Okay, so this matrix P, this 2 by 2 matrix P has orthonormal columns, and that's here. And then the assertion is that Q has orthonormal rows. Okay, so now the point is that the singular value decomposition, it has a lot of nice properties. It it has useful properties. It tells you useful things about your matrix, and I'm going to discuss a few of them. The first one is that the image of A can be easily read off from the singular value decomposition. As a matter of fact, the columns of P are an orthonormal basis of the image of A. Kind of neat. And just by taking the transpose, you see that the image of A, that has a basis consisting of the rows of this matrix on the right, this Q transpose, are an orthonormal basis of the image of A transpose. So it's often the case that when you're handed a matrix, you're asked for a basis of the image, and here it's handed to you in a very nice way. You're even given an orthonormal basis of it. So in our example, the image of A is the column space of A, which is spanned by these vectors, which is all of R2. And you see that the columns of P, these things with the 1 over radical 2's, are indeed an orthonormal basis. Here's P, and here its columns. These are indeed an orthonormal basis of R2. On the other hand, the image of A transpose, that's the row space of A. Well, let's see, the row space of A has these two vectors in it, 1, 1, 0 and 0, 1, 1. And the orthonormal basis of this is provided by the two rows of Q transpose, which is to say this thing 1 over radical 6, 2 over radical 6, 1 over radical 6, and similarly the second row. Okay, so that's one of the really elegant and useful properties of the singular value decomposition. It has a number of other interesting and important properties, but this video has already gotten pretty long, so I think I'll stop there. But I'll just mention that next time what I'll talk about is the notion of condition number of a matrix, and also pseudo-inverse, which are also related to the singular value decomposition.